Okay, let us begin with this theorem. Suppose f is an element of this space, that is all square integrable functions minus pi to pi. Let f suffix n of x be given by this expansion a naught plus summation k equals 1 to n a k cos k x plus b k sin k x, where a k and b k are the Fourier coefficients of this function f, which is a square integrable function. Then f suffix n heads to f in L2 over the interval minus pi to pi as n goes to infinity, which means the norm between fn and f, the integral norm, this heads to 0 as n goes to infinity. So, this is what the statement of the theorem is. Consider a square integrable function, let fn be the Fourier expansion, then this expansion heads to this function in the L2 sense. That means the L2 norm of fn minus f heads to 0 as n goes to infinity. Of course, if you are little careful about it, you might sense that f, this function, is in L2. We have to say that in some way we can approximate this function by a piecewise smooth periodic function. If we somehow get it in that form, then we can approximate that function, the original function, by a piecewise smooth periodic function, and approximate the piecewise smooth periodic function uniformly by the Fourier representation. There are two parts to this, right. I mean, all your discontinuities can happen, though it is square integrable, you may have discontinuities and you will have to extend them carefully, right. So, we will see these aspects carefully, but let us get a feel for the sketch of the proof. The proof sketch involves two steps. First, show that any function in L2 over the interval minus pi to plus pi can be approximated by a piecewise smooth periodic function g, and then approximate g uniformly. And we saw the theorem that if it converges uniformly, therefore it converges in L2 by its Fourier series. So, we need to get an idea towards 1 . We have already established 2, right. The second part we have already established. Suppose it converges uniformly, then it converges in L2, right. We have established this result already. So, let us get the idea towards 1. An element f belonging to this space, which is a space of all square integrable functions, may not be continuous. Even if it is continuous, its periodic extension is often not continuous. There are plenty of such cases. A good example is f of x equals x over the interval minus pi to pi, right. If you define f of x equals x, we saw the points of discontinuity. Now, let us just take a sketch of this. We have minus pi, pi, 2 pi, 3 pi, and so on. So, we have something like this, let us say and this is a discontinuity point, there is a jump. Similarly, if you take a periodic extension, you have the same problem. So, let us form another function g of x that agrees with f of x at all segments except on segments connecting the continuous components of f. This is very important. So, let us form another function g of x that agrees with f of x at all segments except on segments connecting the continuous components of f, right. So, this is a continuous component, this is a continuous component. At these points g of x is going to be differing from f of x. That is the whole idea, right. Let us see what we could do. So, revisiting this minus pi, pi is 2 pi this is 3 pi. Now, here I am connecting them and I am making them continuous. Okay. So, I think you can see I am putting these, I am joining these segments and I am making them continuous. We are fine if we choose, this is very important, a differentiable periodic function g of x such that the norm between f and g in the L2 sense is less than epsilon for a tolerance epsilon, right. This is the first step, right. You try to make it, you choose a periodic function differentiable as well such that in the L2 sense f minus g, this norm, right, in the L2 sense is within epsilon, right. I can choose such a function. Now, with this we have to recall from our last theorem, that is one of the previous theorems. Let us recall the following. The Fourier series of a piecewise smooth 2 pi periodic function f of x converges uniformly to f of x on the interval minus pi to plus pi. So, let g n of x be equal to C naught plus summation k equal to 1 to n ck cos kx plus dk sin kx, where ck's and dk's are Fourier coefficients of g of x, right. We know how to extend the function f of x to g of x, right, that we choose a differentiable periodic function and extend the function original function f, which was just square integrable, but possibly discontinuous at certain points, right. Now, from the theorem above, we can uniformly approximate g of x by some g n of x, right. And how do we do that? By choosing a large positive n naught, we can set, I mean with the Fourier expansion, g of x minus g n of x, the absolute value of this is less than epsilon for all x in the interval minus pi to plus pi. This is very important because it is uniform. Now, the norm of g n minus g square in the L2 sense is integral minus pi to plus pi absolute value of g of x minus g n of x square dx, and this is minus pi to plus pi, this is epsilon square dx, which is 2 pi epsilon square, that is for n greater than n naught. Now, therefore, the norm of g minus g n is basically bounded by, I mean if you choose this to be equal to, if it is within tolerance, norm square is within tolerance of 2 pi epsilon square, this norm is, if you choose some epsilon, you can meet it with epsilon times root 2 pi, right, straightforward. Now, let us consider the norm of f minus gn, that is, we had our original function f, which is in L2, but which possibly had discontinuity points, etc., right. This norm I can write it as follows: f minus gn is basically, I add and subtract g into it, is familiar trick that one does. Now, we apply the triangle inequality, this is f minus g norm plus norm g minus gn, this is because triangle inequality, and this we said is less than, I just put a less than here, less than epsilon, this is less than epsilon times root of 2 pi for n greater than n naught. Now, g n of x is a linear combination of sin kx and cos kx for values k equals 1 so on till capital N. So, therefore, G n of x belongs to the space V n. Now, it is easy to interpret this because from an earlier lemma f suffix n is the closest element from the space V n to f in the L2 sense, right. So, from our earlier lemma, earlier result, f suffix n is the closest element from the space V n to this function f in the L2 sense. So, therefore, if you look at the norm f minus f n, f suffix capital N, this is less than or equal to norm f minus g n, this is less than epsilon times 1 plus root of 2 pi, which means given a tolerance epsilon, we can get as closely as we can to the original function belonging to L2 using the Fourier expansion. So, this is an important result. Okay, I think this is sort of summarizing the various modes of convergence and basically trying to tell that if you are given a function which is possibly suppose you are not able to achieve pointwise convergence or uniform convergence, basically look at the weaker form of convergence, which is basically in the L2 sense. And for you to get towards L2, so take a function f which is belonging to L2, it may have discontinuities, but extend that function using a differentiable function, right, and correcting those points of discontinuities through a differentiable function and periodically extend that, right, and you can figure out such a g which is close to f within a tolerance epsilon, and then use uniform. If you can do a uniform approximation, then you can show that that result will converge in the L2 sense, and then we are home for good, right. And how do we get the function g itself is a construction process which is not discussed in the proof of this result, but if you can do that, then the rest of the result is valid. Okay. So, this gives us an idea that Fourier expansion is quite generic enough. We can figure out, we studied the convergence aspects at a point of discontinuity, at points where it was continuous it was no problem, but we had subtle issues where we had to link the Dirichlet, we had to bring the Dirichlet kernel and look at some subtle aspects where those points were differentiable, right. And then we looked at the L2 convergence aspects, and I think we have sort of summarized the convergence aspects of the Fourier series expansion, and this is a very useful tool for expanding signals in the Fourier space, right. And I think you can think about a similar expansion in the wavelet sense. You have all these aspects that you will have to deal with. I mean, you remember in one of the theorems which I left it as a theorem without a proof, that you can expand this in terms of the direct sum spaces in the limiting form, and when you have to look at the limiting form, then you have to look at all the subtle aspects at points of continuities, at points of discontinuities, etc. You can sort of take a lot of analysis in this work and think about in the wavelet expansion as well, right. I think you now get a very clear picture as to how to expand functions using basis and what are the subtle aspects. Particularly you are in trouble if you have jump points or discontinuity points, and I think this is where you have to spend a little bit of thought to carefully see in what sense it converges. Okay. So, with this we are done with this module on Fourier expansion. Our next lecture would be on KL. Okay. So, we can stop here.